we came across the lecture of our metallurgy subject. Just we'll go for a revision of the same, and after that we'll go to the next articles of metallurgy, that is effect of the alloying elements in the steel itself. So first we'll go for revision of iron carbon diagrams. So already you have seen last time how to draw the iron carbon diagram. So once again I will repeat here. Here is the temperature line. This is the temperature line, and horizontal axis percentage of carbon. Means iron carbon diagram, it is the graph of temperature versus carbon percent. Okay. After this, in this horizontal line, we can divide initially into two parts. 0 to 2, one part, 2 to 6.67, next part. So 0 to 2% carbon, this is called steel. 0 to 2% carbon, this is called steel. And 2 to 6.67, this is called cast iron. Correct. So we have to divide this iron carbon diagrams into two parts, steel and cast iron. Okay. After that, 0 to 2% carbon, again you have to divide it into 0 to 0.83 and 0.83 to 2. So initial part called, it is hypoeutectoid. 0 to 0.83, it is called hypoeutectoid, and 0.832%, it is called hypereutectoid. You see the spelling eutectoid. Two words are taken from Greek language, eutectoids and eutectic. So this eutectoid, hypo up to 0.83, hyper above this and up to 2. Okay. Similarly, because in this here is the hypoeutectoid point. Here is the hypoeutectoid point. Next three, 2 to 6.7, again it is divided into 2 to 4.3 and 4.3 to 6.67. So initially it is called hypoeutectic because here is the eutectic point. So initially hypoeutectic, next hypereutectic. Okay. So eutectic, this is related to cast iron, and eutectoid, this is related to steel. Okay, up here it is clear. After this, you have to go into temperature marking. So temperature marking, initially temperature you have to mark here 210 degrees. This is one temperature. Then second temperature 723. 723 degrees centigrade. After this, next temperature 910. After that, the next temperature 1147. After this, temperature 1400. Then here 1492, and here is 11537. This is actually melting point. Means iron will get melt at this temperature. Iron will get melt at this temperature. Now, in these diagrams, what actually we are expecting? Pure iron is there. In that pure iron, if you go on adding the percentage of carbon, heating and cooling, what structure you will have to see. The study of that structure, it is nothing but iron carbon diagram. Once again, I will repeat, in this iron carbon diagram, what things we get? Pure iron. Pure iron means Fe. Pure iron, if you go on adding percentage of carbon, what structures you will get at a different temperature after heating and cooling. This is the heating and cooling. Okay, which structure you will have to get. The study of that structure, it is nothing but iron carbon diagram. Why there is need to study this structure? Because on this structure mechanical properties depend, and mechanical property it is useful for design development of product, and product reliability is depends upon the mechanical property. Mechanical property it is depends upon the structure. That's why there is a need to study the various structures in the material itself. Okay, so once we have marked this temperature 1, 2, 3, then 4, 5, 6, 7. 7 temperatures you have to remember. Okay, so initially you can make one dotted line. This is called A0 line. What will happen at this line 210? The magnetic changes will occur. Magnetic changes will occur. So in this magnetic changes, ferromagnetic and paramagnetic changes will occur. This you have to mark. Means in this iron carbon diagrams, only at this temperature the certain magnetic changes will occur, that you will have to change. This is called A0 line. Okay. After this, at 723-degree temperatures, you can mark one line. So this line, it is called A1 line. This is called A1 line. Correct. So A1 line, this is also called critical temperature line. A1 line, this is also called critical temperature line. Corresponding temperature is 723-degree temperature. Okay. After this, what you have to do, you have to take this point 910 and corresponding the carbon percentage 0.83, means this line and this line is joined together. This point is called Eutectoid point. This point is called Eutectoid point. Means at Eutectoid point, percentage of carbon is 0.83. 0.83. Okay. And at this point and this line, you have to join. After this, one thing you have to remember, at 0.03 carbon percentage, you draw vertical lines, it will get meet here, and from this point you have to draw this line. Okay, after this, from this point you have to draw one line, but here is the gap. So this gap indicates the carbon percentage 0.008. 0.008. So within this part, you will have to see the structure ferrite. Alpha ferrite you will have to see here. Okay. After this, from this to this, okay, you have to go to the next temperature lines, means here. This you have to draw. Okay. So you can draw abruptly up to here, but at 2 carbon percentage, draw one line. So this line and this line will meet together here. Okay. And from this you have to draw this one. Okay. And after this you can draw one line from the carbon percentage 4.3. So here is the eutectic point. Here is the eutectic point. After this temperature 1462. Okay. So draw one line. So within this liquid plus the Fe3C is there. It is not useful to us, but even though you can draw to this line. Okay. After this, you come to this side. You come to this side at this temperature and 0.1 percentage carbon. You have to mark this 0.1. This value you have to remember 0.1. Okay. So from this point, you have to join line this and you have to join line this. Within this, you will have to see delta ion. Within this, you have to see the delta ion. And from this point to this point, you have to join. Okay. After that, you come to next carbon percentage 0.16. Okay, you can draw this. So within this, you will have to see the delta plus gamma, delta plus gamma. After this, you come to 0.2, 0.5. So draw this line. Within this, you will have to see the liquid plus delta. So at this point, it is called peritectic point. Peritectic point. So here you will have to see some reactions at the left side. So what is peritectic, what is eutectoid, and what is eutectic? So if you see the summary of this diagram, initially we have to heat this. At this stage, you will get liquid, whole liquid, pure iron. Okay, but if you go on adding carbons and step down, you will have to see the one structure. Now, initially here is a liquid. If you come down to this temperature, here you will have to get liquid plus delta. Correct? Delta iron. Okay, our allotropic form of the iron diagram, you might have seen what is that delta. So here liquid plus delta, here you will get the delta iron, here you will get gamma plus delta. Okay, so at this point, this is the peritectic reaction. Now if you cool down, then you will have to see this is the gamma, and this gamma structure, it is called austenite face-centered qubit. So when we cool down within this uh, carbon percentage, then you will have to see here within this column ferrite plus perlite, and after this you will have to see perlite plus cementite. Means from here you will have to see the perlite plus cementite. Okay, perlite plus cement. What is the perlite? It is the alternate layer of ferrite and cementite. Alternate layer of ferrite and cementite. Okay, so here the cementite means Fe3C. Ferrite means the carbons plus iron having less percentage carbon below the 0.83. So you will have to see the here ferritic perlitic structure within this, and after this perlite plus cementite. If you go in this side, below this line, you will get this gamma plus liquid, liquid plus Fe3. Means this is not that much useful. If you cool down below this eutectic point, then here you will have to see the austenitic plus cementite, means gamma plus Fe3C. Okay, and if you cool down again, you will have to see the perlite plus cementite. So below this, this is actually structure we require. Below this critical line. Okay, so here is the A1 lines, here is the A3 lines, and here is the ACM line. ACM means cemented line. Okay, so line numbers A1, A3, and ACM. These three lines are very important. A1, A3, ACM. A2 is also here, but it is the within the alpha plus delta. This is also liquid. So here you will have to see the reaction A2. Okay, but this liquid is not that much useful. But if you cool down below this useful structure, you will have to get. Okay, so you have to remember below this critical line and between 0 to 0.83, you will have to see the ferrite plus perlite, and above this perlite plus cementite. What are the reactions? Here I have reaction. Eutectic reaction. Eutectic reactions means what? So this will occur in eutectic reactions. This will occur in the region of our cast iron. So what is the eutectic reaction? Liquid. So this is the liquid. Above this point, it is a liquid. So if you cool down at this temperature, 0.3% carbon, 1147 degree temperature, then you will have to see the austenite plus cementite. Means eutectic reaction, this liquid is converted into two solid at this temperature. This is called eutectic. This is called eutectic. This whole liquid, it is converted into two solid at this temperature. This is called eutectic. So that's why this is the reversible reactions I have written here. Reversible reaction. Percentage of carbon here is given. Austenite plus cementite. Okay. Next reaction, Eutectoid reaction. This reaction. So here's this austenite. This is one solid. FCC structure means one solid. This austenite at this temperature, at this carbon percentage, ferrite plus perlite, ferrite plus perlite. So this reaction will occur. This is called Eutectoid reaction. And next, the peritectic reaction you will have to see here. So peritectic reaction. So here is the gamma reversible at 1492 degrees centigrade, 0.1 temperature. Here it is there. So it is a liquid plus delta. So here you will have to see the liquid plus delta. So here the liquid plus delta you will have to see. So this is the peritectic reaction. Peritectoid reaction is also there, but it is not shown in this diagram. Now, if you observe what is the austenite and ferrite structure. So here's the austenite, it is face-centered cubic. Ferrite, it is body-centered cubic. So here's you will have to see the ferrite structure, and this round shape, this is called austenite structure. Means this ferrite plus austenite you will have to see here. Ferrite plus perlite. Ferrite plus perlite you will have to see here. Okay. Then cementite plus perlite you will have to see under microscope. And here is austenite to cementite. Means this it will get. This is the number, let us see A. So here's A numbers you will have to see here. A number A. Then cementite plus perlite. Cementite plus perlite here will see B. So here is also B. Okay. And here's ferrite plus perlite. Here C. So here you will have get C. And here austenite plus ferrite. Austenite plus ferrite here. Austenite plus ferrite. So within these regions, you will have to get D. So this structure A, B, C, and here D, like this structure you will have to get under the microscope. So this is about the iron carbon diagram. So still anybody having any doubt, you can ask me. Anybody having any problem related to this diagram? This is very, very important. Now, how it is visible, you can see it is visible clearly. It is visible clearly. Hello? Hello?
Yes, sir.
Anybody can give the answer? It is clearly visible to you or not? Okay, thank you. Any doubt? Any problems? Or shall I repeat? No need to repeat or repeat.
No problem, sir.
Okay, thank you. So we'll go to the next point, that is the effect of alloying elements. Okay, so I will remove this now. So next our point, that is effect of alloying element in steel. So this is the next point in our chapter number 2, effect of alloying elements in steel. Okay, so already we know that in iron carbons we have seen the steel and cast iron. Okay, so what will effect if you add certain alloying element, means extra element just like molybdenum, vanadium, chromium in that steel, what will affect? In simple way, effect of alloying element in steel in simple way, mechanical property will going to change. In one sentence, effect of alloying element in steel, very simple, by adding the alloying element just like chrome, nickel, molybdenum, tungsten, like this, the mechanical property of that steel will going to change. This thing you have to remember. So let us discuss about the first point, but before that I will make a graph. One graph. Here, so this is the hardness, and here is the alloying element. Alloying element, and from this the phosphorus, we take phosphorus, here you can add silicon, here you can write CMN. Okay, here is the molybdenum, here is the nickel, here is the tungsten. So first effect here I will write solid solution strengthening. So let us be consider the first effect, that is the effect of alloying element in steel. So here is the graph of hardness versus alloying element. So first effect, solid solution strengthening and hardening. Most of the alloying elements are soluble to ferrite to some extent and form solid solution, and it is hardened and stronger than pure magnesium. Okay, so ferrite alpha, this is the ferrite, this is also called alpha. In this, if we add certain elements like phosphorus, silicon, manganese, molybdenum, nickel, tungsten, and chromium, what will happen? The strength of this ferrite. Initially, ferrite is very soft. Always you have to remember whenever carbon percentage is very less in pure iron, that iron is very soft. Once again, I will repeat, whenever carbon percentage in pure iron is, that iron is very soft. If you go on adding carbon and allying element, the structure like ferrite, alpha ferrite, the strength and hardness. Strength and hardness means resistance to the load. This will get increased by adding the alloying element. This is our first effect of alloying element. Next, formation of carbides. Next, formations of carbides. Carbide. And you know that carbide is very hard. Carbide cutting tools normally used in our workshop, used in industry for cutting purpose, because that carbide, it will remains at that hardness remains stable at high temperatures, and material will get cut because of the hardness. So formation of carbides. So here some of the alloying elements combines with carbon in steel and form respective carbide. These carbides are hard, increase wear resistance, abrasive resistance of steel. So if you combine this steel plus chrome, manganese, tungstens, molybdenum, vanadium, and titanium. So if we add this element in the steel, means ferritic steel, formation of carbides means very hard material you will have to see. So this carbide means steel combines with this aluminum element, it will become hard, wear resistance, and abrasive resistance. So hard, wear resistance, and abrasive resistance, this you will get in the steel. So if we add this chrome, manganese, tungsten, molybdenum, vanadium, titanium in the steel, it will form carbide, and that carbide is very hard. Wear resistance is more, abrasive resistance. Examples, our cutting tools, our CNC, VMC, whatever cutting tips are there, we can manufacture by using this one. Okay. Then formation of intermediate compounds. Third point, formation of intermediate compound. Intermediate compounds means already we have seen solid solution, two types, completely soluble in each other. Okay, and here one is interstitial solid solutions and second is substitutional solution. But away from these two, one of the things will occur. This is intermediate compounds. Already we have seen in the first chapter what is that intermediate compound. So in this, if we combines with the chrome or if we combines with tungsten, you will have to see the, this is not solid solution, these are the compound. Compound means just like powders. Okay, and formation of intermediate compound, this is very brittle and will get increase that brittleness, and so it is undesirable. Okay, even though in the wear resistant property we can use, extremely hardness will get increased. Our powder metallurgical part, it will comes under this part. It is hard, very brittle. If you see the product of powder metal is just like our brake lining. If you see the brake lining, that is very hard. If you hammer that part, it will get break. Means here brittleness is more. Brittleness is more. Brittleness is more. So it is undesirable away from the certain parts, but it is useful in the powder metallurgical parts. Okay, so here brittleness is more formation of the compound. This is the one of the effects of the alloying element. Now next fourth point, that is the formation of inclusions. Formation of inclusions. So now this iron may combines with oxygen and form oxide when added to steel. Example, if you go on adding here silicon, aluminum, then Mn, chrome, vanadium, and titanium. So if you add this formation of oxides, formation of inclusions, they may combine with oxygens and form oxide when added into steel. Here's some of the aluminum oxide powders are there. For etching purpose, we can use this. So here's inclusion formation part will be there after adding these aluminum elements in the iron. Okay. Then next, the shifting of critical temperatures. Shifting of critical temperature or change in critical temperature. Change in critical temperature. So in iron carbon diagram, we have seen by increasing carbon percentage, the critical temperatures will going to change, and the lowering of critical cooling rate. Next part, cooling rate get will lower in our eutectic reaction. Cooling rate lower means slow cooling will be there. And last ones, austenite and ferrite stabilizer. Austenite and ferrite stabilizers. So these are the effect of the alloying element in steel. So this is one of the articles in our syllabus. What is the effect of the alloying element in steel? In your oral question also, this part will be there. What is the effect of the alloying? In one sentence already I told, to increase the mechanical property. What is the effect of alloying element? To increase the mechanical property, maybe hardness, maybe strength, okay, or maybe the brittleness, whatever the mechanical properties are there, that will going to increase. So which points under this you have to study, you have to draw this graph. In this graph, if we increase, for example, this is the molybdenum, okay. So initially at this point, hardness is low, but if we add the alloying element like molybdenum, so if you go on increasing molybdenum, corresponding hardness will get. If you go on increasing molybdenum, corresponding hardness will get here like this. So if you increase the alloying element this much, you will get this much hardness. If we increase the magnesium this much, you will get the hardness this much. Correct. If we increase the chrome corresponding hardness will get. Means less possibility to getting the hardness by chrome. But molybdenum, Mn, phosphorus, silicon, if we add this, hardness definitely goes on increasing. So this graph indicate by adding the alloying element, hardness will get increased for particular alloying element, it will get decreased. If you add chrome, hardness very less. If you add tungsten, hardness is more. Nickel more, molybdenum more, Mn more, silicon more, phosphorus more. But up to here, range is here. If we increase further phosphorus, no effect of this. So here, phosphorus you can add up to this percentage of phosphorus, you will get corresponding hardness. So once the hardness will get increased, strength will get increased up to certain level. After increasing hardness, it will become brittleness. Okay. So this graph indicates particular element what actually I shown on this figure. The hardness, it will get increasing by increasing the alloying element. Under this certain point is there, by adding, this is general statement, by adding this alloying element, whatever solid solution is there, okay, so that solid solution strength, tensile strength. So what is formula for tensile? Sigma, this is equal to force upon this. Force upon this is tensile. This tensile will get increased by adding this alloying element. This is first step. Second, formation of carbides. Okay, so steel plus, if we add this element, you will get formation of this completely carbide. Strong bond is there in carbide, and it is normally used in our cutting tool. And for this, hardness is more, wear hardness is there, then abrasive resistance is there. Next, formation of metallic compounds, just like powders form. So here's Fe plus chrome, you will get one compound, and this is very brittleness. You will have to see the powder form. Okay, in our powder metallurgy, this thing is very important. Next, formation of inclusions. If any place we required certain oxide formations requirement, then you have to add this element and Fe, formation of inclusions. Okay, inclusions you will have to see in our oil bearing, means impregnated soil bearings are there. There we require inclusion, means small holes in that oil will get introduced, and for this purpose lubrication is not required. Okay, so this bearing, self lubricating bearing, we are using such type of the including devices. Then change in critical temperature. In our iron carbon diagrams, we have seen the A1 line. This is critical temperature line. By adding this, temperatures of the critical temperature, it will go on changing. It will come down below the 720 degrees. Then cooling rate. Regarding this cooling rate, slow cooling is there, not drastic. Drastic cooling, what will happen? If you heat any part up to certain degree temperature, directly cool, what will happen? It will get cracked. So not to get a crack, for this purpose, we required to add certain alloying element in steel. That's why the cooling rate is very slowly, the crack formation will not be there. So these things we will have to see in our heat treatment part. Then austenite and ferrite stabilizer is there. So within that iron carbon diagrams, this alpha plus delta we have seen. So this will become stable. Okay, so in order to make this stable, we require to add certain alloying element. But actually this and this, it is not useful. After cooling down, it is useful. But this ferrite plus austenite, normally cooling, we get ferrite plus perlite, and this is also very fine structure. Okay, so these are the 7 effects of the alloying element in the steel. Okay, this is the points. Clear? Anybody having any doubt related to this? Anybody having any problem? Hello?
No, sir.
Okay, very nice. Thank you. In your orals, one question always be there. What will the effect of the alloying elements in the steel? Very simple. Mechanical property will going to change. What is your answer? Mechanical property will going to change. Okay. Thank you. So shall I remove this? Hello?
Yes, sir.
Okay. Thank you. Now third points for chapter number 2. That is the plain carbon steel. Plain